Hey, Mark. Good to hear from you, sir. Although your email address, I gotta say, is a little weird, but I figured it out. So, I wrote out some stuff here and I'll do the rest by hand. First, I said, I'm not going to do your homework for you, so I'm going to change the question slightly. You asked, you buy a plastic dart gun, why would you not? And being a clever physics student, and you are, you decide to do a quick calculation to find its maximum horizontal range. You shoot the gun straight up and it takes 5.6 seconds for the dart to land back at the barrel. What is the maximum horizontal range of the gun? So I wrote here, instead of 5.6 seconds, let's make it 8.4 seconds, okay? So imagine that being 8.4 seconds. As usual, also, we're going to ignore air resistance and other ways to lose energy and be in our magic physics world where everything works nice. So, first question I asked here is, if it takes 8.4 seconds to go up and come back down, how long does it take to get to the top? Pretty obvious. 4.2 seconds. Half the time to go up, half the time to go down. So what does that do? Ah, my friend, if I know that t equals 4.2 seconds to go up, I also know Vy final at the top is 0. For a split second, I come to a stop. And I know that Ay is negative 9.8 meters per second squared, good old gravitation due to gravity. Then, or acceleration due to gravity. What did I say? Gravitation due to gravity? I'm still rusty. I can find the initial muzzle velocity of the gun. We'll end up with Vi equals Vf minus At. We'll get 0 minus negative 9.8 times 4.2. You would do this with your 5.6 divided by 2, my friend. And when I crunch the numbers, I get positive answer, which is good. I get 41.16 meters per second. That's my muzzle velocity. That's what this gun can launch a projectile at. Then the next question is, when do I get my maximum range? Well, I'm going to assume that we're starting on the ground because the question doesn't mention a height off of a cliff. If we're starting on the ground, the maximum range, as any good athlete can tell you, is when you launch the projectile. Come on. Sorry. Still getting my computer warmed up after the summer. Oh, that was a little strange. Try that again. There we go. Whoop. Come back. Still getting my computer warmed up after the summer. The maximum range, if you're shooting from the ground, is when you shoot it at an angle of, hey, what would make sense? Think about it. Oh, pen acting up. 45 degrees. If I shoot at an angle of 45 degrees, that's when I'll get my maximum range. This is not good here. There we go. Haven't tried running this program all summer. So, this is a job for components. I have 41.16 meters per second. I have an angle of 45 degrees. I'd like to find my initial vertical and my horizontal. Well, my horizontal ends up being V cos theta. It ends up being 41.16 times the cosine of 45. My horizontal ends up being, what am I going to get here? 29.1. My initial vertical, and once again, of course, I would ask, why did I put an initial on the vertical? Because the vertical is changing, but the horizontal is constant. We're talking about a projectile. That ends up being V sine theta. And it ends up being 41.6 times the sine of 45. And because the sine of 45 and the cos of 45 are actually the same answer, you also get 29.1 meters per second. Now it's time to break this up into horizontal and vertical. So here's my horizontal. Here's my vertical. Horizontally, I can say Vx equals 29.1, AX equals 0. Vertically, I can say VY initial equals 29.1, and AY equals negative 9.8. Well, this isn't enough to get me anywhere. I need something else, because I said you need 3 things to find the fourth, and you may have clued in by now that we're looking to find t time. So, let's see here. Oh, I know one more thing. I know my vertical displacement. How high was I started? How high was I when I started? On the ground. How high was I when I finished? On the ground. What's my vertical displacement? 0. So now I can use dy equals vy initial t plus a half ay t squared. Oh, this is looking pretty good here. I'll get a quadratic 0 equals 29.1 t minus 4.9 t squared. Now you can solve this using the quadratic formula if you wish. Good old x equals negative b plus or minus the square b squared minus 4ac all over 2a. Or this one, it turns out, actually factors. There is a greatest common factor. There is a t in every term. This factors into t bracket 29.1 minus 4.9 t, which means, if you recall, that either t equals 0 or 29.1 minus 4.9 t equals 0. For something times something to give you 0 as an answer, one of the factors, or both, have to be 0. Well, of course, t equals 0 is an answer. It's saying you were on the ground at time 0. But t also equals 4.9 plus the 4.9 t over. Try that again. Plus the 4.9 t over. So you'll get 29.1 divided by 4.9. 29.1 divided by 4.9 on my calculator sitting next to me, and I get 5.9387 blah, blah, blah. You know what? I'm just going to leave it like that. I could get a decimal answer, but this is going to go over to the wonderful world of horizontal. I now know t equals 29.1 divided by 4.9. How's that help? Well, hopefully by now you kind of see where I'm going with this. This is your maximum range. It's going to be 29.1 times 29.1 all over 4.9. Now, I'm noticing I could probably generalize this. The fact that there's two 29.1s here suggests that as long as theta equals 45 degrees, then the maximum range is Vx squared all over, well, that's half of, that 4.9 is half of 9.8. How can I half of 9.8? Well, I could go half of AY, but dividing by a half, hey, that's the same as multiplying by 2. This looks kind of familiar. Am I seeing kind of a VF squared equals VI squared plus 2AD? Get the, I don't know. I'd have to muck around with it. Anyways, if you want an actual answer, it's going to be 29.1 squared divided by 4.9. So my answer for the example that I made up is 172.8 meters. Then I would go back and I would adjust the sig figs. This is probably a 2 sig figs, so I would say 170. So hopefully you can redo this with t equals the original time, which was 5, which whatever the heck it was. All right, my friend?